Well, the Indian Space Research Organization has shared a video now of Chandrayaan-3's mission Pragyan rover as well, playfully frolicking on the lunar surface. The video captured by the lander's camera shows the rover rotating in search of a safe route. Now, this came after Pragyan rover travelled a distance of approximately 15 meters and captured a snap showing the Vikram lander after it also met with a crater in its way. The Indian Space Agency has released several images captured by the Pragyan rover. Not just this, another instrument on board the rover confirms the presence of sulphur in the region. Through another technique, the alpha particle X-ray spectroscope has also detected sulphur as well as other minor elements. The spectroscope has detected the presence of sulphur on the moon using a distinct technique. Let's in fact take a closer look at the same with our guests. Joining us at this point are Srijan Pal, CEO of Homi Lab. We also have Dr. Mila Mitra, Earth scientist and astronomical science specialist, joining us live. Group Captain V.N. Jha, former Joint Director DRDO, also continues to be with us. So let me quickly go across and explain to our viewers what exactly this new image in fact is, and then I'd also urge our guests to join us over here. Srijan Pal, if you can please be with us. Dr. Mitra, I'd also request you to come as well here, because the fact is, let's quickly now, could we go to the first slide please? Let's go to the first slide. Yes, here's the first slide. So ISRO has revealed that Pragyan covers 15 meters of distance. So far, the kind of roving that has been done by the rover is 15 meters of distance from where the lander landed on the moon. Srijan Pal, would you like to talk us through this, the distance that so far the rover has been maneuvering under? Right.
So the rover has gone 15 meters. It goes at a maximum speed of about 1 centimeter a second. So it's relatively slow for obvious reasons.
Yes.
Do understand that the gravity on the moon is 1/6. So it's not as easy to navigate because you feel less weight, 1/6 the weight. So it's harder to navigate. And we saw how craters did come in the way. A 4-meter diameter crater had to be evaded and went around. So it's going around, it's finding its ground. It's all it's more or less a preconceived path, but do understand that not all of this is algorithmic driven. A lot of the time the Pragyan rover gives a signal to Vikram, and then Vikram sends it to Bangalore, and then Bangalore tells Pragyan what to do. So it is still human controlled, partially AI driven. It has got 2 cameras on its 1 megapixel, 2 cameras to guide it wherever it is going.
Approximately, where do you think it's fitted, the
No,
cameras?
this is the Vikram.
This is the Vikram. Okay, so yes. So the rover would be somewhere here. Yeah.
Right. So it's there.
Okay.
And of course, the Vikram has got, now coming to Vikram, it has got 4 cameras on either side.
That's also, yeah.
Yes, so 4 cameras on either side. So the shots of Pragyan, which you see, are coming from one of those 4. Whichever direction it is going. What you should also see in the pictures which we saw earlier was that the shadows are getting smaller now. The initial shadow was really long. Why? Because the day is rising. So as the sun is rising in the horizon, the shadows are getting shorter. One challenge while it is going, wherever it is going, is Pragyan, unlike Vikram, does not have solar panels on all 4 sides. So it has to find the direction so that the sun shines on its panel and the energy thereby is created.
Yes.
Today we saw the whole frolicking thing. I think ISRO has also got a great sense of humor now, besides everything else.
True.
So this is the path of Pragyan.
Let's go across to the next image, the next slide if we can. Let's try and go across to the next imagery. So yes, so Pragyan clearly can capture images of the lander from about 15 meters away. That's what we've been seeing so far, those images that have come in from day 1 itself. And if we can go to the next slide, the next image, which will of course give our viewers another sense, another aspect of the data that has come in so far. Okay, so interestingly earlier, Pragyan had come across a 3-meter diameter, a 4-meter diameter crater as well. So remember, interestingly, even before the landing, already we were seeing pictures of the possible landing spots on the South Pole, and we could see a lot of craters on the moon. Interestingly now, Dr. Mitra, I'd like you to come in here. There's been a 4-meter diameter crater that interestingly Pragyan has also come across.
Yes, so today it came across a crater, and it was given the commands to avoid it. And like he said, the commands are not completely autonomous now. What Pragyan rover does is it takes images with its imaging cameras and sends it back to Bangalore. And of course, there's a time delay involved here. And then Bangalore gives it instructions on how to move. And so today we saw an fun image of the rover rotating around because it was trying to avoid this crater. And this happened on 27th August also. It was given instructions to retreat, and it successfully retreated.
Because there are multiple such craters, obviously.
There are multiple craters, and it can navigate small craters, and it has. But if there's a bigger crater, it might land.
Does this fall in that?
Yeah, this falls in that.
Okay.
And also the rover has very slow speed in addition to less power.
Yes.
So if it falls into a rover, it may not have to a crater, it may not have the momentum to come out of it.
Okay. Okay. Well, let's try and go across now to another image. And so, yes, so this, of course, was that crater which was positioned 3 meters ahead of its location, which is obviously something that had to be navigated by the rover and was done successfully. Let's quickly go across to the next slides. Yes, so here the rover now was then commanded to retrace the path. So here is another image. Obviously, this is the surface of the moon. And these are commands being given, aren't they, interestingly? And, you know, okay, before, just hold it here, just pause it here. Yeah, I want you to come in on that image of the craters, Srijan.
Maybe we should go to the previous slide.
Yes, yes. You can explain it here.
So craters are typically, what are craters? Craters are depressions in the ground.
Yeah.
How are they made? They are made usually by giant meteors striking the lunar surface. Now on moon there is no atmosphere, so nothing burns. So there's no shooting stars which you can see from moon, because everything just falls on the surface. The southern pole, the area we've gone, is full of such craters. Why are these craters interesting? So the question is, why we even go there, right? Because these craters also provide shadow areas where freezing temperature would remain for billions of years. And that is why those craters are actually useful for us. So you saw in the previous image, the track was changing. The track, it keeps changing, and this is largely driven by Bangalore. So the Bangalore-based team is constantly monitoring. So somebody is driving this, and as ma'am was saying, 2.6 seconds it takes for crater to send an image to Vikram, Vikram to send it to Bangalore, Bangalore to send a signal back to crater. So 2.6 seconds is the reaction time. Minimum reaction time is 2.6 seconds. So you understand that that's why the rover has to be slow as well.
Yes.
So this is, we can see.
Okay, now, yeah, let's play this out now. Let's play this, if we can. So ISRO has shared this image and this is that fun image. The rover is seen locating a safe route. Obviously, it's locating a safe route because there are a lot of these craters, which, as Dr. Mitra said, it has to navigate.
The camera images, while it's going around, it sounds like a frolic. But actually, what it's trying to do is that take a 360 image of where it is. And that image is being going to Bangalore.
And this and this rotation is being captured by the lander's camera.
The Vikram. Vikram camera.
So one of those Vikram cameras.
One panel, one side, whichever side it's facing, the side which is facing will have a camera which is seeing this.
Yeah. Vienja, you want to come in here on the, obviously the rover trying to locate a safe route, which is why this rotation is happening, and this is obviously all being captured by the lander's imaging camera.
Absolutely. Look, this is extremely important. Maneuvering rover safely is very, very tricky job, because suppose in one of those craters or smaller craters or the depressions or the ridge, if it topples, you can't retrieve it. I know you can't make it straight. It would be extremely difficult task thereafter. So and these are not the time for that automated landing where you don't have reaction time. Here you have reaction time. Rover and lander both are taking the picture of the terrain ahead. You know what is there. You know where to go. And then ISRO has got the time frame. You mentioned 2.6 seconds. That is the least time for the signals to travel. But add up the human cognition part of it, that when the information comes to you, you want to analyze, and you are in no hurry. It's not that jet propulsion or landing thing that you are getting into difficulty. Here you have got time. So look at those data coming to you, look at the pictures, and then you take a concise decision with you or your team of ISRO scientists who are maneuvering the rover around. So that's extremely important to avoid any crater which may cause it to topple down. That must not happen. And secondly, I'm very glad that even the lander, you can see, which is standing, giving a shadow, but it is landed in a way that the solar panel is absolutely getting the sunlight there in that. So suppose if it would have landed another, say, about 100 or 90 degree on the other side, it would have been slightly slant light coming onto that, and of course the other side, the other 180-degree side of this also would have generated the energy. But these are the small intricacies that a lot of consideration must have gone into at the time of design, at the time of that automated landing, that all these should be done there thoroughly, and then that is how all these has happened. And of course, now in this phase, ISRO has got time. That they have got. There is no day, there is no night at the lunar surface. That night will only happen after another 5 terrestrial day, Earth days, when it will go into the night time. So till that time, it has got time, and I'm sure ISRO must be doing everything that is possible, that it had designed that lander and the rover to conduct those experiments. And entire nation, the world over, everyone will be celebrating that yes, these raw data or the data from that area of the moon is coming to the Earth for the first time, wherein all world scientists can have look at all these data. So compliment to the ISRO for maneuvering all this, and there is no hurry right now. They have got time. They have got time to think, and they have got the time to make a decision.
Okay, yes, I've got some more imagery now that I want to quickly bring up here for our viewers. So now we are going to shift our focus to the sulfur findings. So APXS has emitted alpha particles, and if we go across to our next slide, which will help explain this, the particles have interacted with the atoms in the soil. So this is obviously the procedure to gauge what all minerals are there on the surface of the moon. The interaction obviously causes X-rays to be emitted, and this obviously is helping in decoding the information to the ISRO team. The X-rays have been very, very helpful in decoding the information for the ISRO team. So that's been the procedure so far, isn't it, Srijan?
Right.
And Dr. Mitra, you can also come in, both of you, on gauging what all minerals are there. Be it sulfur, be it oxygen, be it aluminium, all that has been discovered so far.
So there are two things by which, two processes, two equipments. One is the LIBS and one is the APXS. The LIBS uses lasers. It fires that at the material, at the sample, which is somewhat the regolith. This is regolith. Lunar soil is called regolith. It fires that, and when the gas comes out because of the laser, it does spectrometry on it, and it finds out the particles. This one, the APXS, has a sort of a radioactive element within the equipment, which fires alpha particles. Alpha particles are fired, same thing happens, but here it doesn't vaporize, it lets out a corresponding X-ray. Each substance has its own characteristic X-ray. That X-ray is analyzed, and based on that we find what is the element which is present there. Now the beauty is that both of these tests are doing the same thing, but in science you do two things from different ways to see consistency, and we saw consistency. Sulfur, for instance, was found by both. Now sulfur is very interesting. Why is everybody talking of sulfur? Sulfur could have come in two ways.
Yes.
One is, long ago there were volcanoes on moon, which means those volcanoes were going out. But there's quite a lot of sulfur, which means the volcanoes might not be that old, which is very interesting, which is suggesting that maybe the core of the moon has cooled off rather recently and not that old as we were thinking about.
True.
Or something even more interesting has happened. Sulfur can bind with water. So it can go with water droplets, and it could be frozen. It could stay frozen for billions of years. And if that water vapor someday got the radiation from the sun on moon, it will vaporize. And then the sulfur would be released, which means sulfur is your prerequisite. It's sort of a sign that there is water nearby. That's why everybody is getting so excited about sulfur. Because what is happening on the 9th day is
that
sulfur.
Could be the next step.
The next step could be somewhere nearby, somewhere hidden would be water. Interestingly, China's probe, the Chang'e 5, which also did a lunar return, has suggested there is somewhere around 6,000 billion kilograms of water on the poles. 6,000 billion kilograms, which is where our Chandrayaan also said something similar.
Yes.
So the search for water and hydrogen is the most important search which we are doing on moon now.
Dr. Mitra.
So yeah, I just want to add to what he said
and
is that
obviously the procedure, yes, this APXS and the LIPS, what you were talking about earlier, these are all part of the rover's mechanism.
So the rover is doing the experiments in situ, as we have called. So it's going to locations close by and using its laser and its X-ray to take the measurements. And as he said, we have found sulfur and we have found other traces of elements like iron, like oxygen even, but we have not found hydrogen yet. So that is one of the key things still remaining to that we would be looking for. And as you know, the lifetime of Chandrayaan-3, the rover, and is only till August 7th. So we just have a few more days.
September 7th.
September 7th. So we have a few more days.
So the countdown is on, Group Captain Jha.
Yes, countdown is on, and it will continue. Look, Uday, what I'm really thrilled is, and what India or ISRO will be thrilled, or the world is thrilled, is we are looking at the South Pole from the window. That window is open. This time we have only sent, say, 6 sensors from the Earth to do the study. Next time, maybe there could be 16 or 60 sets of sensors doing various other things. So this is the very basic instruments that we have sent. I'm glad that sulfur has been found by both alpha particle spectrometer as well as the laser spectroscope. Both are corollary in some way, not exactly. One is finding the elemental form of it, looking at those bandwidth, and another is, as Mr. Srijan explained, that alpha particle is doing in another way. But alpha particle analyzer is doing more of a study of the chemical composition of the soil, that regolith. And the laser breakdown procedure that can even send the laser wave deep into the rocks and then do the analysis also. So, both are active, both are working in the perfect condition, and both giving the same thing, similar sort of feedback, confirms that yes, there is no error, sulfur is there. And this has to be continued. And the last but not the least, what I am looking at is, I only hope that the laser breakdown procedure has got the open-end logic also into it. Usually when we feed into the recognition of the material, we feed in a closed loop sort of thing, that if you find this type of wave, identify it as a sulfur or the iron or the titanium. But what happens if you don't find that type of wave?
Yes.
Usually, a closed-end instrument ignores those data. I only hope that ISRO has kept it in the open-ended, so that tomorrow, in the tomorrows, maybe 1 year, 2 years or something, you look into those open-end data and try to analyze.
Okay.
Are we looking at the 109th or 110th component?
Group Captain Jha, Srijan, and Dr. Mitra, thank you all for joining us with your perspectives on this big story.
For more such videos, subscribe to the NewsX YouTube channel, hit the bell icon.